Hello, this is Team 26013 Automated Guided Vehicle. In industrial manufacturing and warehouse environments, heavy machinery, framework, and raw materials are constantly being moved around. This poses a couple of challenges. There's safety risks, as human operators usually face hazards from lifting, transporting, and positioning these multi-ton loads. There's inefficiency risks, as manual forklifts and cranes require trained operators and need space constraints in order to move around safely. Caterpillar came to us asking us to help with this problem.
The primary objectives of this project were design a system capable of lifting up to 2 metric tons, achieve autonomous navigation using line following, ensure safe operation with emergency and detection systems, maintain a maximum speed of approximately 3 miles per hour, and successfully integrate the mechanical, electrical, and control systems.
Our design approach combined research, analysis, and iterative prototyping. Mechanically, we developed a steel frame capable of supporting high loads, supported by FEA analysis to verify structural integrity. For lifting, we implemented a hydraulic system designed to generate sufficient pressure and stroke to lift heavy plates. Electrically, we selected battery systems, motor controllers, and a microcontroller to power and control the AGV. For navigation, we developed a line-following system using sensors to guide autonomous movement.
Some system requirements for this project is that our prototype AGV must be able to lift a 2 metric ton load with a factor of safety greater than 2, at least 6 inches. This lift time must be greater than 12 seconds and less than 60 seconds. Our AGV shall also be able to detect obstacles greater than 1.5 times the largest part dimension, must stop within 1.5 times the largest part length, have a turning radius of 1.2 times the largest side of the AGV, have visible lights, an audible buzzer, follow a predetermined path, all under a budget of $4,400.
Our final design consists of 4 major subsystems: a reinforced steel frame for structural support, a hydraulic lifting system capable of raising heavy loads, an electric drivetrain enabling controlled movement, and a sensor-based navigation and safety system. These systems were fully integrated to create a functional AGV platform.
To verify the performance of the AGV, we conducted multiple tests during and after building. Some of these tests include drive testing at controlled speed, braking tests, autonomous navigation testing, hydraulic lifting tests with 50-pound mock loads, and then later hydraulic testing at Caterpillar's Tucson Proving Grounds at the full weight of 2 metric tons. The results from each test were recorded and later compared against our design requirements to confirm system functionality. All of these tests validated our system requirements, and it was determined that our AGV was a successful project.
The results from our verification are as follows. We were successfully able to lift our target load of 2,000 kilograms at the measured height of 6 inches, or 150 millimeters. The lift tests were timed and passed both the minimum and maximum amounts allotted for raising and lowering. Stress and strain measured using gauges during verification are extremely accurate to our FEA predicted model analysis, with a standard error of around 1 to 2%. We have adequate speed control and braking performance using our drivetrain, and our sensors provide 360-degree awareness during operation.
Throughout the project, we faced several challenges, including integrating the electrical and mechanical components together while not having to change the design, hydraulic system design and finding the correct fittings to make sure the system operates effectively and safely, and navigation and wiring reliability to power AGV while facing strict deadlines for our verification tests. From these difficulties, we learned how to be adaptive to sudden changes in our plans and to think of new strategies in a constrained time frame. Learning to manage these difficulties in this project prepares us for these rigors and higher stakes events that we could face in industry. Many of these challenges helped us develop lifelong problem-solving skills and improve our engineering process that will benefit how we work in future engineering projects and endeavors.
Safety was a critical part of our design for our AGV. Some features built into the AGV for safety are emergency stop systems, sensors for obstacle detection, and controlled operational limits to ensure safe use. During building, safety was also a top priority. Gloves were worn when handling metal and wood, nitrile gloves were used when handling chemicals and paint, safety glasses were worn during cutting, welding, grinding, and hydraulic testing, and gloves and welding helmets were worn during welding.
We would like to thank our sponsors, our mentor, and Caterpillar for their support throughout this project. Thank you for watching.